Thank you, Matthias, and welcome everyone. I'm Cailler, and today I will introduce you to a work done with Parosh, Mohamed, Chencheng, and Philipp on how we can use GNN in order to solve a word equation problem. And in particular, I would like to thank Chencheng because she was the PhD student who did a lot of work, and we should thank PhD students. So first of all, thank you for coming. I know that being the first talk of the last day it's not the most convenient spot. So thank you for attending. And the talk of today will be about word equations. So word equations are equations made of letters and variables. And the main idea is to find whether they are sat on or sat. So for instance, we have this word equation here, and we want to find a substitution that makes both sides equals. And in that exact situation, with x maps to a, y maps to a, and z maps to b and b, both sides becomes equals. So this problem is satisfiable. Nice. Now what interested us in that work is conjunctive word equation, which is a conjunction of word equations. In that situation, the word equation is satisfiable if every sub-equation is satisfiable and unsat otherwise. So as soon as we have one of the equation unsatisfiable, then the whole thing is unsatisfiable. And once more, if we take this example and the same substitution as before, then the whole thing becomes satisfiable. Great. So now that we have this, it sounds kind of simple, but we have more difficult example, and in particular, this one with only 7 different variables and 7 different letters. When we try to solve that with a state-of-the-art leading solvers, they fail in a reasonable time. So 5 minutes is a reasonable time in that situation. And at that point, we just tried to figure out whether using machine learning for this kind of situation could be useful. Okay, so I missed my transition, but okay, this kind of problem is difficult for solver, and word equations are basically difficult to solve because even though the problem itself is decidable, its exact complexity isn't known yet, but it's in NPR and at least in free space. And usually practical implementation are incomplete in order to achieve good performances. So we have to drop completeness, which is hard, but at least it works in practice a little bit. But word equations are important, especially for check user input or string manipulation. And this is why we tried to see whether machine learning can help us solving them more efficiently. Okay, so usually people in formal method aren't super happy with machine learning. So don't worry, it's not just another talk about how can we use ML for this specific problem. Well, yes, sometimes we also think about things while doing this job. Also, does it work? Well, yes. So yeah, good thing, it works. And easy maintenance over now, not entirely. We have some room for improvements that the machine cannot achieve yet. So on the more technical part, yes, this is the big picture of the work. So we have the word equation here. So phi1 to phi n are word equation, and this is a conjunctive word equation. Then the first step when we try to solve it is to rank them. So we can reorder equation in a different way, mainly in order to find unsatisfiable ones at the very beginning. And then after the reordering part, we split to deal with each word equation independently. And we try to solve them. So if one word equation is unsatisfiable, then the whole thing is unsatisfiable. Otherwise, if one word equation is satisfiable, maybe with a substitution, then we broadcast the substitution to other branches. And if all branches are satisfiable with one common substitution, then the whole thing is satisfiable. This is how we do first ranking and second split. And this is where it happens, because we use GNN for ranking equation, and then for splitting, because when we have to deal with one word equation, we can apply different rules. And basically, we ask GNN, okay, here, how can you reorder equations? And here, okay, which rules should I apply first? I assume you many all have a little bit of insight of what is machine learning. And in this work, we in particular use graph neural networks, so GNN, which are neural networks that are designed to work with graph structure data. They take a graph, one or more graph as an input, and they output also a graph. And in particular, they are very useful to capture the structural feature of a graph. And this is what's interesting us because our data here and our problem was very easy to represent as a graph. So we use GNN, and we start by addressing this problem, so the splitting issue, how we can use GNN to find to solve one word equation. Okay, so this was a previous work with the same people, and it was mostly implemented in a solver, so Dragonly, which is also the name of a cat. This is why you will see a cat often in the slide. I also love cats. I don't think it's important here. So Dragonly uses the Nielsen transformation, which is a set of splitting rules. And basically, it consists of taking the first element of each word equation and iteratively apply rules on them in order to discard them. And when there are, and for each word equation, you have multiple rules that can be applied. You can choose one. For instance, here we choose x up to y, and then you can discard both variables and just continue with the rest of the equation. Dragonly also makes use of iterative deepening and backtracking. And yeah, that's it. So for the rules of the calculus, there are three main cases and 7 rules in total. The first case is when there is 2 letters at the very beginning, so L and L prime, and in that situation, either they are equals. In that situation, you can just discard them. Either they are both equals to either both words are just equals to the empty string, and so in that situation, we can just say that the equation is satisfiable. Either they are different, and then you can just conclude unset. For the case in which we have a variable and a letter, there are 2 situations. So in the first one, we can just map the variable to the empty string, and so we discard the variable on the first string, and we continue with this equation. Or we map the free variable to the letter of the second equation, concatenate to another fresh free variable, and then we continue with that. And finally, for the case of two variables at the beginning, either they are the same variables, so in that situation we can just discard them. Either they are different, and we have 2 rules which are symmetric. So we map one variable to the other one plus an additional fresh variable, and we continue. Or we just map a free variable to the other one. We discard both, and we continue with the rest of the equation. So those are our 7 rules. And in order to provide training data to the GNN, we generate a graph. So how to read this graph? On each node, so there are 2 colors. Green color means that this node can lead to a satisfiable assignment. The red one means that there is no it's unsat. And there is also the equation we want to deal with on the top. And at the bottom, there is a number here. So here it's 2. It's the idea of the node, basically. And 14 here is the size of the subtree, including the current node. So here, for instance, 2, because 2 nodes. Okay, and it's satisfiable. On the edge, you have which rule was applied. And basically, for each word equation, we generate a full graph like that. We add with every rule applied each time. We loaded it with the size of the subtree, and we train the GNN in order to find the shortest path to a SAT. So in this example, the GNN would be rewarded if it chooses this path. So this was our set of training data. And now that we have this, we also need a way to represent a word equation, because as I said, it's a GNN, so it works well with graph as an input. So we could have done, just give the word equation like that, but it's more efficient if we give it in a graphical way. And so we choose to represent the equation like that, with the equal symbol at the root node, and then both equation on the side. And we also add some structural information with additional nodes, such that each equation, each variable points to the variable, and each letter points to the letter. And yes, that's it. And this is what we gave to the GNN. So a graph representation of the equation, the corresponding proofs of tree, and then the GNN learn at each branching point which rule it should prioritize. And so when we give it a new equation, it will just predict, okay, at this point you should choose this rule first. Okay, so this was how the whole things work for this problem. We implemented this into Dragonly. Dragonly was made in Python, so Dragonly wasn't made for performances at first. There is no complicated heuristic or so on. It was just made to be a baseline and to see whether machine learning can help. For this problem, it was focused on SAT, because if a word equation is unsat, we have to check every path anyway, so it doesn't make any sense to use GNN in that situation. And the results are quite good, because it provides results comparable to state of the art solver, which makes us very happy. But after that, we tried to improve this in order to be able to deal with multiple equations, so conjunctive word equation. And also, we would like to improve our solver on unsat problems. So now we will focus on this class, how to deal with multiple ones, and also how to improve in unsat. And our way to improve with unsat is to rank equation such that unsat equation will be managed first. Because if you find one unsat equation, then you can deduce that the whole thing is unsat very quickly. So why does order matter? Well, if you take, for instance, this equation, the first one is quite complicated. So if you start by this one, you will time out quite easily. But if you start by the second one, A equals B, you will find directly that it's unsatisfiable. And so this is why we wanted to reorder them. In Dragonly, we didn't just do a basic search first. We also had some naive heuristic, let's say. We first started by managing equations that are already empty string equals empty string. Then we manage equations such that the empty string is equal to something else. Then equations such that the first two letters are different, then when the first two letters are equals, and then the rest by priority order. And when multiple equations have the same priority order, we just choose the shortest one first. And this was the basic heuristic of Dragonly. And our main focus here was to deal with the otherwise part, like all the other equations, and to see whether GNN can provide us some hints. So for the third, when we tried to see what can help the GNN, we talked about a minimal unsatisfiable set. So for a word equation, a minimal unsatisfiable set is a subset of the conjunctive word equation, such that all the equation is so that it's unsatisfiable, and if you remove one equation, it becomes satisfiable. It's not unique. You have multiple MUS for one equation. For instance, in this one, A equals to X and X equals to B, that's enough to conclude that this equation is unsatisfiable. But we could also have choose AA equals to XA. So we have multiple options here. And so we decide to use MUS as training data. So in order to generate our training data, we first took 20,000 problems. We gave them to Dragonly, and for the problem that Dragonly wasn't able to solve, we gave them to other solver, like the three, the Twinkler, 55, Osterreich, and Worch. And because giving the problem that Dragonly already solved to Dragonly doesn't make any sense, so we only use other solver, and we extract the MUS. And once we have this MUS, we label equations that we have to label equations. For equations that are not part of the MUS, their score is 0. And for equations that are part of the MUS, we only label the shortest one in the MUS as 1, because when we ask Dragonly to rank equation, or mostly the question we ask is, okay, which equation can make the whole thing unsatisfiable? It will only choose 1. So it was, empirically speaking, more efficient to only label one equation as 1. So 1 is the equation Dragonly should choose. So only the shortest one in the MUS, and yes, so this is our training data. And since we now deal with conjunctive board equation, we also have to improve the graph representation of equation. And once more, we tried multiple ways to represent them. So at first, we tried to do only one big graph, but it was just too big for the GNN, and it wasn't that efficient. So we choose to encode each equation on its own. So here we will only give only two equations, but since they are connected, we need to also add some global information. And then we choose to add the information of the number of occurrence for each term and variable. So here, for instance, X appear 3 times in total, Y twice, and A 5 times. And in order to represent how many times they appear, we choose the binary encoding. So the binary encoding of 3 is 1, 1, of 2 is 1, 0, and of 5 is 1, 0, 1. And we represent them as nodes like this: V0, V1, and V1 for variables, and T is for terms. Once more, we did multiple tries, such as unary encoding, ternary encoding, and also decimal encoding. And empirically speaking, this one gave the best results. So we gave all that to Dragonly, encoding of equation and the MUS, in order for it to train. And then when we want to call the solver, we just gave it a new conjunctive board equation, and Dragonly provide us a sequence, a reordering this equation. Okay. Among the questions that are often asked when we talk about that, why do we train a second GNN? Mostly it's because it's a completely different task. The first one has to focus on SAT solving, on defining a SAT assignment, and also it has a fixed size of input, and it has only a fixed set of rows. While this one has to deal with the varying size of the input. We doesn't have all the time the same number of equations and so on. And it has to focus on NSAT, so there are two different GNN. About the encoding, it's mostly after empirical evidence. For the graph, in particular, a unary encoding would increase the size graph way too much for the GNN to use it efficiently, and for more advanced encoding like ternary or more, the coding would be too small and it will blur the structural distinction, making the whole GNN inefficient. And finally, when you call the GNN, also here we tried multiple things, and what works best was to call it only once at the very beginning instead of calling it each time. Because it limits the overhead, but we also try to call it each time so the question was find SAT and so on, and empirically speaking, it works well. So this is what we did, and in order to test our method, we did some experiments. So we start with remote benchmark for SMT-lib and the Binder. But since Dragonly was quite simple, we don't manage things like a length constraint, Boolean operator, and regular expressions. And so our final benchmark was too easy. So we had to generate our own benchmark. For this, we took world equations such that like that. So they are equals at the very beginning with a length of at most 60 letters. So 60 here and 60 here that are to command a set of letters T. And then we replace a letter n times. We replace n times some substring of a world equation in both parts by m variables. And finally, we took between 0 and 100 equations. And one particular notion here is the linearity. So we said that a conjunctive world equation is linear if and only if each variable appears at most once in each equation. So this one is linear, x and y are unique. Here to see linear too, because okay, x appears twice, but only once in each equation. And this one is not linear because you have y in both sides here. Okay. And then we generated 4 benchmarks. So for A1, it was each time we introduce a new variable, it's a fresh variable. So this benchmark is linear. For A2, it's mostly like A1, but more difficult. So we have more terms. We replace more substrings, and we also have fresh variable. Then we have benchmark B, which is like A1, but there is no fresh variable. So we only took variables from a given set at the beginning, so making it non-linear. And finally, for benchmark C, we have equation of this form. And in this one, each B is replaced by an equation of A1. So it's highly nonlinear. We run Dragonly as well as other solver on them with a 5-minute timeout. This specification. Also, when we train Dragonly, we train it with 60,000 problems per benchmark. And for the evaluation here, we only have 100 problems per benchmark per experiment. And so the results were quite nice. So in A1, for instance, Dragonly performs the best result, so satisfiable, unsatisfiable. Our benchmark is mostly made of unsatisfiable problems, indeed. So Dragonly performed quite well with the best in both categories, SAT and unsat. Also, it has fewer splitting than other versions of Dragonly, which is nice. Yeah, here is the Bavi version. Here is a random Dragonly, so we just randomly reorder equation, and this is Dragonly with GNN. So here, GNN performs well. On A2, Dragonly solved the most problems in total, so SAT and unsat, even though it's not the best one in each individual category. For benchmark B, unfortunately, when we go to non-linear benchmark, performances drop a little bit. So it's only competitive, but random gave better results. So it was a little bit disappointing. And finally, on a very difficult benchmark, Dragonly apparently wasn't super happy with that because the GNN version wasn't able to solve anything. Meaning that on non-linear problems, Dragonly calling the GNN doesn't help that much. But for linear problems, it provides good results and also fewer splits than other versions of Dragonly. Also, the fact that Dragonly doesn't perform well on very difficult benchmark, it's because other solvers often make use of dedicated strategy, like based on the question length or letter count that we didn't have in Dragonly. We also think that implementation can offer improvements, and also we try increasing the data set and Dragonly perform better with more data. So maybe increasing the data set even more can make it even better. So yes, finally, in this work, we extend Dragonly to handle conjunctive word equation. In particular, with a multi-classification task to handle variable number of inputs. We use NUS and a new graph representation to do so, and it provides good results on linear problems. And now we would like to optimize the GNN overhead. Maybe we can think about the call timing, so when to call the GNN, maybe more than once, maybe once every 10 iterations. And we would like also to add something like length constraint or regular expression. Thank you.